When you add heat to any material, it becomes hotter. But how much hotter? Well, that depends upon the material itself. So if I take a little bit of heat and add it to, let's say, iron or silver, it becomes hot instantly. But I take that same amount of heat and give it to water, well, the temperature barely changes. These are materials with very different specific heats. And that's very, very important for practical considerations in engineering, in physics, in biology, everything. And so we will understand this quantitatively. But specific heats can be very different depending upon whether you take that material and you force it to have a fixed volume or you put it under constant pressure. Now, if you put it under constant pressure, then we will need to discuss a quantity. It's very convenient. Chemists use it all the time, called enthalpy. After that, we'll look to see what kinds of machines actually measure specific heat, because that is something important across the board. But first, we need to get a quantitative measure on how much heat a body absorbs. Let's add heat to a system, any system. We shall put a small amount of heat, delta Q. Now, this is to be measured in joules or whatever unit of energy that you're using. As a consequence, the temperature is going to rise by some amount. Let's call that delta T. And for now, both delta Q and delta T can be assumed to be small. So if you added the heat to this water, it gets a bit hotter. Take the ratio of delta Q to delta T. This is what is called the heat capacity. And it's literally that, the ability to absorb heat. So when you add delta Q, the temperature goes up by delta T. If delta T is small, then obviously C is going to be big. It's going to have a big heat capacity. So adding the same amount to two different systems is going to lead to different increases in the temperature. And that will depend upon several factors. First of all, the mass of the substance or the system. So if you add delta Q to a small amount of water, the rise in temperature will be greater. If you double that mass of water, then the rise of temperature delta T will be only half as much. So bigger things have greater heat capacity. Makes a lot of sense. Every time that you add delta Q, the temperature will not go up by amount delta T. It could be more, it could be less. And that's because most systems are nonlinear. So water at lower temperatures has a different heat capacity as compared to water at higher temperatures. Then the heat capacity also depends upon the external pressure. How exactly? Well, that depends upon what's inside. And then the heat capacity depends on whether you allow the substance to change its volume or not. Now let's try and understand what happens at the microscopic level. So as I said earlier in my introduction, it helps if you know the substance at the atomic or molecular level. So take ice. Now ice is water molecules which are bonded together in this way. This is a hexagonal structure, and the melting of ice means that these bonds have to be broken. So then you can have fewer bonds. Now it's going to take energy to break these bonds. If you give more energy, in other words, if you add more delta Q, then of course the water molecules are then going to be able to escape from each other and turn into steam. Now let's be a little more precise about what various heat capacities are. CV is called the heat capacity at constant volume. So suppose you keep the system's volume constant. You've added in an amount of heat delta Q from here, but you have not allowed this piston to move. So this is at constant volume. On the other hand, I could have allowed this piston to move, so it has moved up a certain distance. And that means that this system has done work against the external pressure. So the atmosphere is bearing down on this, and this system has worked against the atmosphere. It's pushed the piston up, and so this system has done work. Well, where did that work come from? It came because you added in that extra amount of heat. So now we can ask, which of these two heat capacities is likely to be bigger, CV or CP? And when are they almost going to be equal? Well, it's pretty clear that CP is going to be bigger than CV. Why? Because you have to put in more heat in order to make this piston go up. According to the first law of thermodynamics, which is the conservation of energy, you cannot get work for free. You had to put in this extra amount of heat. So in that case, this delta Q would have to be bigger in order to get the same rise in temperature. So that's saying that if you take the ratio of Cp to Cv, call that gamma, and we'll need this later, well, that gamma is going to be bigger than 1. That's pretty obvious. Now let's look at Cv and the relation to the internal energy U. Well, the first law of thermodynamics says that the increase in the internal energy of a system is equal to the heat put into the system plus the amount of work done on the system. Now, in this first case, where the volume doesn't change, no work is being done by the system or on the system, and so delta W is 0, which says that delta Q is equal to delta U. And so that says that CV is just delta U over delta T. And this is provided that the volume be held constant. So the way to indicate that is you take the partial derivative of the internal energy with respect to the temperature, holding the volume constant. So that's the first case over here. Now remember that U is a state function. So U depends upon the temperature, pressure, and volume. And it's actually a function whose partial derivative you can take. But remember, take it keeping the volume constant. Well, what about Cp? And how is it related to the internal energy? Here, again, it is the first law of thermodynamics, and that says that delta Q is equal to delta U minus delta W. Remember that delta W is the work done on the system, not by the system, but the work that you did, not what the system did. That makes a difference in sign. So, of course, then Cp just becomes, when you divide by delta T, so look over here, delta Q over delta T, and delta Q is just this, so you divide this by delta T, and delta U by delta T minus delta W by delta T is what? Is Cp. So we have an expression for Cp over here, just like we had an expression for Cv over here. But in this case, I could write this as a partial derivative. Here I cannot, because W is not a state function. I don't know how to differentiate W. To overcome this, there's a quantity that is called enthalpy. Chemists use this quite a lot. Enthalpy has the symbol H, and H is defined as the internal energy U plus the product of the pressure into the volume. Now, this was defined more than 100 years ago by Camerling-Ons in 1909. Let's see what we can say about H. First of all, it's pretty obvious that its dimensions are those of energy, because you're adding energy to energy, joules. Secondly, it's an extensive quantity. So just like heat capacity doubles when I put twice the mass, similarly, the enthalpy will double. So if I double the mass of the system, then U is doubled, and of course, H then doubles. And of course, if I'm doubling the system, then the volume is doubled. Pressure remains the same. Pressure is what is called an intensive quantity. So, extensive, extensive, extensive. How should one think about PV? Well, you remember that when you do work against an external force and you change the volume by a small amount, dV, then the work done is P into dV. And so PV is like the external work that was needed to create the system. Why did chemists define this? That's because they do their experiments at fixed values of pressure. For example, suppose you have a substance over here and you want to investigate it. Well, you will investigate this under the conditions of normal atmospheric pressure. Now, suppose this sample melts and it increases its size. Well, if it increases its size, it's going to push the atmosphere up, which means that it is going to do work. And so the amount of heat that you will need to melt that substance will be different depending upon whether you allow this to move up or you don't. So, of course, the heat capacity is going to be affected by the value of the pressure. And you know that for example, water. It boils at a different temperature at sea level, and it boils at a lower temperature when you go high up into the mountains. Now let's look over here at the definition of H. H is the sum of a state function plus a function of P and V. Well, it's a pretty simple function of P and V. It's just the product of P into V. And so H is itself a state function, meaning that it depends upon P, V, and T. Now let's see what happens if we make a small change in U, in P, and in V. In that case, delta H will be just the change in U plus V delta P plus P delta V. Now, in an experiment like this one over here, you don't change the atmospheric pressure. That's a given constant, or almost a constant, because the pressure is different today as compared to tomorrow. But it can be assumed to be reasonably constant. So delta P is set equal to 0. And so in that case, the change in H, delta H, is then just delta U plus P delta V. But from the first law of thermodynamics, this is equal to delta Q. So read it as this. Delta Q is equal to delta Q minus P delta V. And minus P delta V is equal to delta W. You remember that you have to make a difference between your doing work on the system and the system doing work upon the outside environment. So anyway, this is the first law of thermodynamics, and we simply have delta H is equal to delta Q. So in other words, when you add an amount of heat delta Q, the enthalpy goes up by the same amount, provided the pressure is constant, which means that we've got what we wanted. The heat capacity at constant pressure is simply partial H by partial T at constant pressure. So now we do have a partial derivative. Now, before I proceed to give examples of specific heat calculations, let's review our understanding of what the chemists call moles. Okay, so here is hydrogen, which has got just one nucleon in it, one proton. Carbon has got 6 protons and 6 neutrons, so it has 12 nucleons. Oxygen has got 16. If you take carbon dioxide, well, carbon is 12, like here, and there are 2 oxygen atoms, and so the total number of nucleons, what we call A, is 12 plus 2 times 16, which is 44. Take something like sulfuric acid. There are 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. So if you just add up, you get 98 nucleons, and so the mass of one molecule of sulfuric acid is 98 times bigger than that of hydrogen. The mass of each hydrogen atom is about 1.66 times 10 to the minus 24 grams. Of course, we know this now to 7 or 8 decimal places. I'm just writing 2 of them over here. That means that in 1 gram of hydrogen, there are going to be so many atoms. 6 times 10 to the power 23 atoms. This is what is called Avogadro's number, Na. And more accurately, it is this. This takes us to the definition of mole. A mole is defined as the quantity of a substance that has the same number of particles as are found in 1 gram of hydrogen. So 1 gram of hydrogen contains this many atoms. So 1 gram of this, 12 grams of this, 16 of this, 44 of this, and 98 of this contain these many atoms. I should say that earlier hydrogen was used as the standard, but these days it is more usual, it's more accurate to base everything on carbon-12. So Avogadro's number is the number of carbon atoms in 12 grams of carbon-12. Now let me come to the specific heats, Cp and Cv. By specific heat, I mean we are now going to take an intensive quantity. So I'm going to take 1 mole of an ideal gas. So I'm going to take 1 mole of an ideal gas while calculating the specific heats. Let's look at the gas law. PV can be written as either NKB into T, or you can write it as nRT. They're the same. nR is the same as NKB, and N is the total number of molecules, is the Boltzmann constant, T is the absolute temperature. It's measured in degrees Kelvin. N is the number of moles, and we've just discussed what a mole is. R is the gas constant. So I said over here, NKB is equal to NR, and so R is then defined as the number of atoms divided by the number of moles times the Boltzmann constant. The internal energy of an ideal gas has a very simple form. It's 3 over 2 NKT, which is the same as 3 over 2 nRT. This can be easily derived from statistical mechanics, but since we haven't studied that as yet, just accept it for now. Now it's very easy to calculate the specific heat at constant volume. It's just du by dt at constant volume, and you can see that du by dt is 3 over 2 R, and remember that we are taking 1 mole of gas, so n is equal to 1. The units are obvious. It is energy, joules, per degree Kelvin, per mole. To calculate the specific heat at constant pressure, we will need the enthalpy. And you see that enthalpy is coming in as a useful concept now. It is U plus PV. And U is 3 over 2 nRT, whereas PV is nRT. Just add them up, you get 5 over 2 nRT. And now let's just take the derivative and put n equal to 1. So dH by dt at constant P is going to be 5 over 2 R. So the usefulness of enthalpy becomes immediately obvious at this point. We can take gamma, which is the ratio of Cp to Cv. It's 5 over 3. And this is a number that's going to come useful to us when we talk about thermodynamic engines. Take the difference between Cp and Cv. Well, obviously, it's 5 over 2 R minus 3 over 2 R. And so that gives you the gas constant R, defined above here. Let's look at some specific heats now. Take various substances. So everything from water to gasoline to plastics to steel, silver and gold has been measured. Let's say that we give 1 unit of heat, and that unit of heat is in calories. 1 calorie is so many joules, 4.186 joules. Let's take 1 gram of each material. So 1 gram of water, when you add 1 calorie to it, then its temperature rises by 1 degree Celsius. In fact, this is why calorie was defined in this particular way. So then, for water, the specific heat at constant pressure is 1 calorie divided by 1 degree Kelvin. Convert that into joules, and this becomes 4.186 joules per degree K per gram of each material. Now you can see that when you added 1 calorie, the temperature went up by only 1 degree Celsius or 1 degree Kelvin. But if I was to add that same 1 calorie of heat to gold, that would go up pretty close to here, to about 31 or so. And so the specific heat for gold is only 0.13, whereas for water, it is this. In other words, water has a lot of capacity to hold heat. Gold has very little capacity to hold heat, and you can wonder why. The reason is that gold has got a lot of free electrons, and these free electrons can move about in the entire gold sample. They can conduct electricity, and because they are light, you need only a small amount of heat energy to get those electrons moving around very fast. On the other hand, if you take water, then water is made up of molecules which are fairly heavy, and they also are bonding with each other, and therefore you will need more heat to raise the temperature up by the same level. So the microscopic structure of matter essentially determines how much the specific heat of something is. And that's actually a very good way of finding out what a particular substance is. Is it gold? Is it silver? Is it copper? Is it steel? What? They have different specific heats. This is why there is a lot of professional equipment, such as this differential scanning calorimeter, that will tell you the specific heats, and then you can determine what a particular sample is, its purity, and so forth. In this diagram, you can see that whichever material you want to investigate, you put that over here. There's something for comparison in this place, and then you supply heat, and then you see how much the temperature of each rises for the same amount of heat. Finally, I want to find a simple expression that holds for Cp minus Cv for any material. Okay, so let's go back to the definition. Cp is dH by dt at constant P, which is, now remember, H is equal to U plus PV, but P is a constant, so I'll differentiate U with respect to T at constant P, and then there's P dV by dt, again at constant P. We didn't need to differentiate this because P is a constant. On the other hand, Cv is du by dt at constant volume, V. So the difference between P and V is that on this side you have this, and on this side you have this. Now here one realizes that U, the internal energy, depends upon the volume and it depends upon the temperature. In other words, U is a function of the volume and the temperature, but the volume depends upon the temperature itself and upon the pressure. Now, du by dt at constant pressure is equal to this. The first term is obvious. U depends upon the temperature directly through the temperature over here, and so it's just du by dt at constant volume. That is keeping this here fixed. Then you keep this fixed and you let V vary. Why does it vary? Because the temperature has changed. So using the chain rule, we have du by dV at constant T. In other words, this T is kept constant. And then how V depends upon T itself at constant pressure. So I've just used the chain rule over here. Let's take the difference between Cp and Cv. So I need to subtract Cv from here. You put that here. And now this cancels against this. So then we get something that's much simpler. It's just du by dV into T plus P times this. And now just to check this, let's see if we get the right answer using PV is equal to RT. Why RT and not nRT? Because we are taking 1 mole of the gas. Now let's recall that U does not depend upon the volume for an ideal gas. So du by dV is 0. That's the 0 over here. P comes here. And dV by dt. So take dV by dt from this formula. That is R over P. So we have P into R over P, which is R. And so we have got it right. This formula applies everywhere for an ideal gas, a non-ideal gas, a liquid or a solid, anything.